Right, so here we go with CCEA, A2 Physics, Unit 2, Fields, Capacitors and Particle Physics for June of 2018. Let's get started. Question 4a. A magnetic field exists around a conductor carrying an electric current. Sketch the shape of the field and indicate its direction due to the current carrying conductor shown in figure 4.1. The direction of the current is indicated by the arrow. So we've got upward current here, and this is a right hand grip rule. So if you imagine you're gripping that, hold your pen or whatever with your thumb pointing up with your right hand. You'll find that your fingers are wrapping around the back in this direction. So they're heading round the back. Sorry, narrower pen. Heading around the back. And they're coming that way across the front. So we should get a circular field with this anti-clockwise direction to it. Part B. Two identical magnets with opposite poles facing are placed on a top pan balance. A wire is fixed so that it is parallel to the magnets and connected to a circuit as shown in figure 4.2a. On figure 4.2a, draw an arrow to show the direction of the force on the wire when the switch is closed. So firstly, let's work out a current direction. We've got a plus here, so current's coming this way, which means it's going across like that. So current is heading this way. Field is north to south, so field is coming across like that. And that means that if we get in our left hand, field lined up, first finger lined up with the field, second finger lined up with the current, you end up with your thumb pointing down. So the answer is a downward force. So you want to show a downward arrow. Part C. Before the switch was closed, an initial balance reading was taken. The switch was then closed and the readings on the ammeter and balance recorded. These readings are shown in table 4.1. Complete the column headed force in newtons in table 4.1 to determine the magnitude of the force exerted on the wire for a current of 4.24 amps. Okay, so you can see here that the mass in grams decreases, and that's consistent with the wire being pulled down. Because the wire's being pulled down, the magnet yoke is being pulled up, so that will reduce the reading on the balance, and that is what's happening. You can see here that it's been reduced by an amount of 0.53 of a gram, and so we just need to turn that into a force in newtons using W equals mg, and that works out to be 0.0052 newtons. Part 2. Determine the flux density of the magnets, and the length of the magnets L is shown as is going to be 5 centimeters. Okay, so we've got a yoke length of 5 centimeters. So this is just a straight bookwork. F equals BIL, and so B is going to be F over IL. So the force is the value from the table, I is the 4.24, and we just need to make sure that L is not in centimeters but in meters. And that comes to 0.0245 Tesla. Part 3. A voltmeter is placed in parallel across the wire between points A and B and reads 0.41 volts when the current through the wire is 4.24 amps. Calculate the resistivity of the wire if the diameter is 0.18. So this is like a synoptic question, bringing back AS stuff. So the resistance of a piece of wire is rho L over A. So just rearranging that for rho then. So rho will be RA over L, and we can get R from V over I, so we can substitute V over I in for R, and rho then becomes VA over IL. And A can be replaced with pi R squared. Okay, so we have a voltage of 0.41 when the current is 4.24. We have an area of pi times the radius. Remember, they've given us the diameter, and the radius is 0.09 millimeters, and then you square that. And the L we already had is 0.05 because it's 5 centimeters, 0.05 of a meter. So we just put all that into the calculator now. And so we get 4.92 times 10 to the minus 8. Obviously, thing to be careful about that question is the units. And that's that. Thanks for watching.